All right, it's 8:30. We're going to get started today. All right, good morning, everyone. Second day of class. How's everyone doing today? Good, doing good. All right, so today I guess is the first real lecture. So on Monday, we kind of just introduced the course and today we're going over. So the plan for today is to go over first order ODE. So I think hopefully this should be reviewed from math to ODE. I'm going to go a little bit fast, but I try to put in as many examples as I could. I think with these math concepts and these math techniques, I think seeing more examples I think helps a lot with practice. So I try to put at least 2 examples of every kind of concept and every technique that I have. All right. So announcement before I begin. Some of you may have noticed I posted homework 1, and so this is not the email time. This is an actual problem set. Homework 1 is posted on Canvas, and so that is going to be due a week from today. Homework 1 is based all on first order ODE. So I'm hoping that we finish everything today or finish our review for first order ODEs. And so after today, you should have everything you need to do that first homework. So definitely take a look at it, definitely get started. If you have any questions on it, I have office hours today. I have office hours Monday and Wednesday as well. And of course, you can always ask a question. All right. And so are there any questions I can answer before we get started for today? Okay. All right, let's go and get started. Like I mentioned, the topic for today is first order ordinary differential. All right, so on Monday, we talked about a lot about what this class is about. So this class is a lot about, how do we, basically take a physical engineering system and put it in a form that we can do analysis with. And kind of the underlying thread behind a lot of what we talked about on Monday is that you need to have a model. So anytime you perform an engineering analysis or any kind of engineering calculations, the first step is to take your physical situation and put it in terms of a mathematical expression with variables. And so if you're able to do this, if you're able to take a physical system and formulate it in math, basically, this is basically what constitutes a model. So you'll hear me use the word model quite a bit in this class. So when I say model, all I mean is that you've taken a physical system and you've represented it with math. Okay. And the benefit of this is that you can use that mathematical expression to basically predict its behavior, to analyze its behavior without having to go and physically actually try it out. Okay. So that's what a model is. And the interesting thing about how our world here is constructed is that a lot of times when you look at the physical quantities that describe a system, a lot of them are derivatives of each other. So as an example, probably the first one that people learn is the relationship between displacement, velocity, and acceleration. Okay, all three of these are derivatives of each other. The velocity is the derivative of displacement, and acceleration is the derivative of velocity. That means acceleration is the double derivative of displacement. Okay? And so because we have so many physical quantities that are derivatives of each other, it just kind of naturally follows that differential equations, which are equations that are formed of derivatives, just show up just really often, just show up really a lot whenever you do any kind of physical model. You can't really escape it. So no matter which branch of engineering that you go into, there's at least one, if not dozens of differential equations that describe its behavior. So there's really no getting away. So learning how to not only solve differential equations, but also analyze solutions is essential in performing any kind of engineering math. So that's why we as engineers we put a lot of emphasis on differential equations. Just because there's this kind of everything. And so let's give some examples. I'm going to take a first order example because that's kind of what we're going over. So examples of some physical behavior. So let's do something very simple first. So if we look at a falling object. Probably something that you learned in your first physics course, right? And normally you don't think of something simple like this in terms of differential equations, but we can form a differential equation. We know that the acceleration due to gravity is 9.8 meters per second squared, right? And so what we can say is that the derivative of the velocity with respect to time. In other words, the rate that the rate at which the velocity of the obstacle is equal to 9.8. It could be just as simple as this. And so this is technically a differential equation because we have a derivative that is equal to something. That's very, very simple example. Let's do something a bit more complicated. One that we'll see later today in the example. Let's look at a linear circuit. So let's have a simple just RC circuit. So we have a capacitor, we have a resistor. And what you can do is that you can look at this linear circuit and form a differential equation based on the amount of charge that's in the circuit. So what you can say is that the resistance multiplied by the time derivative of the charge plus the charge divided by the capacitance, 0. Another case where you have a kind of fairly simple physical system, but again, we can represent its behavior using a differential equation. And so these are just two examples, but you can come up with dozens and dozens more. Maybe I'll do one more. This is an example from heat transfer. I don't think anyone's probably taken heat transfer yet, but you'll definitely experience this at some point. And so in particular, we're going to look at a case of convection heat transfer. Okay. And so what convection basically means that anytime you have a moving fluid, then it's going to cool or it's going to heat a surface a lot more efficiently than if the fluid is not there. Okay. You may have heard of a device nowadays that's very popular called an air fryer. And so part of what makes an air fryer work is that it blows hot air over your food, and it kind of emulates the effect of frying without actually moving oil. Okay, so the idea is that air fryer is it's basically just an oven, but you add a fan to it, and that heats your food a lot more efficiently than just an oven by itself. So what we can say, so if we look at the surface temperature T, then the time derivative of the surface temperature T is equal to minus H times the temperature minus the ambient temperature. So H is something called the convection coefficient. And so that tells you how efficiently the fluid is heating or cooling the surface. And T infinity is the ambient temperature. So these are just some examples. And so I wanted to show you, that differential equation, it's not just a math tool. You are going to see it. If not, you may have seen some of these equations already. Maybe if you take a circuit or maybe you remember physics. And you'll definitely see the last one when you take 407 as well. Okay? The differential equations are everywhere, and so it kind of pays to know how to solve. All right. Any questions on this so far? Okay. All right. So let's define a couple more things. So I've been using this term ordinary differential equation. So let's go ahead and define that. Oftentimes you hear me call it ODE. When I say ODE, I'm referring to an ordinary differential equation. And so an ordinary differential equation is one that contains only one unknown and one independent variable. They might be asking, what's the unknown? What's the independent variable? Right? Well, oftentimes, we'll be using, see me use the derivative dy dx, so dy d. And so in these cases, the y The y is what we're solving for. And so the y is, that is our unknown. And so the unknown that we're solving for is often in the numerator, or I guess you can call it the numerator of the derivative. And whatever is in the denominator, which is the one that we're looking at in terms of the rate of change for, this is the independent variable. Okay, so we should have only one of each. So if you have an ordinary differential equation, there's one unknown that we're solving for, and there's one independent variable that the unknown is going to be a function of. And so kind of the extension of an ordinary differential equation is a partial differential equation where there's multiple independent variables, but those are literally exponentially harder to solve, and we're not going to get into it. Okay, so that's the definition of an ODE. Let's define what a solution to an ODE is. And so normally, if you're looking at like an algebra problem, which is, if you're solving for like x or something like that, the solution to an algebra problem is often just a number, or it's just we call it a scale. In contrast, when you're solving an ordinary differential equation, what you're looking for is not just one number. It's just not one value. It's actually going to be a full-on function. And you should get a mathematical expression most of the time. So you should get a mathematical expression, and that mathematical expression should be a function of the independent variable. We'll do a couple examples that kind of illustrate kind of what I mean by this. And so one useful thing that you can do, and you can do this throughout the entire differential equation section. So today and for the next 4 weeks. And something I really encourage you to do as well is that you can check your answer. And so you can check your answer to a differential equation by just simply plugging it back in. And so if you've had a chance to look at the homework already, you can see that I actually give you the solutions to the, I give you the final solution to the problem. But technically, you don't even need that. And so technically, you can take whatever you find, plug it back into the equation. You can use that to check your solutions. Let's do a couple of examples so you can see how this works. Okay, so let's consider this ODE. What ODE is by dx. You can see right away we have an ordinary differential equation, so there's only one unknown. So unknown here is y in this case, and our independent variable is x. So we have one unknown, one independent variable. All right, let's say that we have this ODE, and I've given you the solution. So let's say I tell you that the solution y of x is equal to 3 over x. And so what we want to check is we want to see if this 3 over x is that if that really is a solution to this ODE. Right, so the best way that we can do this is just simply plug it in. All right, so to plug it in, we need to plug it into two places. So we have y of x. We can just plug it directly into y right there, because y is the same thing as y of x. Okay. And we also need to plug it into this part right here. And so before we can plug it in, we need to take the derivative of this solution. Okay, we have dy dx, so let's plug in y. So it's going to be d dx of 3 over x. Okay. And so we want to take derivative of basically 3 over x. And so the 3 is just a constant, so let's just kind of bring that out. So 3 d dx of 1 over x. And so the derivative of 1 over x, another way that we can express it. A little bit easier is x to the minus 1. Okay. And so from there, it's easy to see how we can take the derivative of this. And so we're going to multiply. We're going to use the power rule. So we're going to multiply them by the minus 1. And so this will be 3 minus 3 times x minus 2. Okay. And so this is going to be a minus 3 over x. Okay. All right, so let's go ahead and plug all that in. And so we're going to plug this in for dy dx. So in our original equation, we have on the left-hand side, we have x times dy dx. So we have x times minus 3 over x squared. And that's equal to minus y. So we have minus times 3 over x. This right here, x. This right here. Right, so let's just simply work through the algebra here. And so on the left-hand side, we are going to cancel out an x. So we have an x up top and an x squared on the bottom. And so that x up top, we cancel out with this exponent right here. Okay. And so on the left-hand side, we have minus 3 over x. And on the right-hand side, we have a minus 3. We have both sides of the equal sign are equal to each other. So we have minus 3 over x on one side, minus 3 over x on the other. And so this tells us that we are all Gucci. And so this tells us that our solution 3 over x is indeed a solution to this differential equation. All right, any questions on this example right here? Okay. All right, so you can do this for any for basically any differential equation, throughout this entire course. So if you're ever unsure, you go through the process. Especially when we get to second order ODEs next week, the process can be a bit long. So if you're ever unsure about your solution, just plug it back in, and so that'll tell you whether you're right or wrong. Okay. All right, so let's go ahead and move on. So let's start with a few more definitions. All right, so let's define this term we call general solution. All right, and so what you'll see very soon is that when we solve differential equations, a lot of times they involve integration. Right? So the opposite of a derivative is an integral. So it makes sense that integrals involve somehow solving this differential equation. When you perform an integral, in particular, if we perform an indefinite integral, a lot of times you have to add an arbitrary constant. And so when I refer to general solutions, these are solutions to ODEs that contain one or more arbitrary constants. And so the key word for this is arbitrary. For example, let's go back to our previous example. So what you might see might often is that your y of x, in the previous example, we saw that we had a 3 up top. But instead of a 3, you might have a c. With this c right here, this c is basically any arbitrary constant. So it could be 3, it could be 5, it could be 7, it could be 1,337. Okay, it could be anything. And a lot of times when you solve a differential equation initially, you can only solve for the solution up to an arbitrary constant. And so when you have a solution like this, we say that the solution is not just one function, but it can in fact be a family of many solutions. Right, so that's the general solution. So oftentimes, when you first solve an ODE, you're going to get a general solution. But the solution is going to be particular up to that arbitrary constant. All right, so the next definition that we'll have is particular solution. Okay. And so oftentimes, it's a little bit unsatisfying to get just a general solution because you do all this work and you get this function, but it can still be infinitely many solutions. And you feel like we didn't really do much of anything. And so when we talk about the particular solution, this is one in which we choose a value for the arbitrary constant. So that instead of a family of solutions, we are now kind of honing in on just one solution that's going to work for this particular problem. And the way that we usually obtain a particular solution is that we take our general solution and we apply what's known as either a boundary condition or an initial condition to our solution. right, so getting a particular solution is usually kind of another step. So after you kind of go through and solve the differential equation, in order to get the particular solution, you have to apply a boundary condition or initial condition. What kind of books? All right, any questions on this so far? Right, so let's get into the actual techniques. And so, we've gone through kind of just general information about differential equations. Let's get into some techniques on how to actually solve some first order differential equations. So there are two main techniques that I want you guys to know from to solve different first order differential equations. The first is called separation of variables. So that might have been the first one you guys might have learned. And the other one is using an integrated method. Let's start with separation of variables. And so that is that belongs to a category of what are called separable ODEs. All right, so first let's define separable ODE. And so first order ODE is called separable if it could be put in this form. So this is kind of what we're looking for separable ODE. Let me define some of the terms in here. First, we have g of y. And so g of y, this is a function of just y. And on the right-hand side, we have f of x. And so f of x, by contrast, this is going to be a function of only x. And so in other words, a separable ODE is one where you can perform separation of variables, okay? And so you want to basically manipulate, oftentimes you have to manipulate it algebraically a little bit, but you want to manipulate so that all the y terms are on the left and all the x terms are on the right. So that's usually kind of what we're aiming for. And like I mentioned, sometimes it's not going to be apparent. And so sometimes it's not going to just present itself as separable to you. So sometimes you have to do a little bit of algebra in order to get it. So what's the benefit of this form? And so the benefit of this form is that, if you can get all the y terms on the left and x terms on the right, what you can do to solve it is that you can simply just integrate both sides to solve. Because if you look at our derivative is dy dx. Okay? I'm going to do something, and it's good everyone here is an engineer. If there's any math people here that might work. This is mathematical sacrilege. Okay? Let me go ahead and I'll rewrite the expression that we have up here. Okay. All right, so a derivative is not really a fraction, but we're going to perform mathematical war crimes here and just pretend that it is a fraction. Okay? And so what I'm going to do is I'm going to take this dx and I'm going to multiply it by both sides and move it over. So d of y, dy, equal to x. That was professor rolling over in his grave. All right, and so now that we have in this form, let's integrate. And so on the left-hand side, we have an integral of g of y dy, and on the right side, we have integral of f of x dx. This is perfect. That's great. But remember, these integrals that we're performing here, these are indefinite integrals, right? The reason they're indefinite integrals is because we don't have any bounds. And so in other words, we're not really performing an integral. We can say that we're performing an antiderivative of these. And so because we're doing an indefinite integral, we have to add a constant. And so technically speaking, we have to add an arbitrary constant to both integrals because they're both indefinite. But when both constants are arbitrary, we can kind of just lump them into one. Okay? So this c right here is an arbitrary constant. This c right here is an arbitrary constant that results from the fact that we did an indefinite. You can't forget that. So that is something that's really important. Okay. But what we'll do is that once we kind of solve for the general solution, so this is going to give us a general solution basically, then we can apply an initial condition or maybe a boundary condition to solve for c. All right, so I'm going to do a couple examples on this so you can see this in action. Before I do examples, are there any questions on this? Okay. All right, so let's go ahead and jump right in. Okay, for example, let's say that we have the differential equation y dx equal to 1 plus y squared. So with this differential equation, let's solve for just the general solution. So we want to find, what is a function y of x based on this differential. Okay. Right. So when you first see a differential equation like this, a first order equation, a good question to ask yourself is this equation separable? In other words, can we algebraically manipulate this equation so that we get everything with y on the left and everything with x on the right? You can do that. We can solve this with separation of variables, and generally it's a little bit faster than the other methods of integrating. If you can solve an equation with separation of variables, that's generally faster. Okay, so let me do this. So let's manipulate this equation, because right now, as it currently stands, we can't apply separation of variables to it just yet. Okay, so we have to manipulate this a little bit. So let me do this. So let's divide both sides by 1 plus y. So I'm going to take that right-hand side of the equation and divide it by that. Okay? So that on the right-hand side, we eliminate y, so there's no more y on the right-hand side. And we've got to move it to the left-hand side. All right, so if we divide both sides by 1 plus y squared, that means on the left-hand side, we're going to have a 1 divided by 1 plus y squared and 2y dx. And on the right-hand side, we have 1 plus y squared divided by 1 plus y squared. Okay. So here we have the numerator and the denominator completely equal to each other, and so those are just going to cancel out. And so on the right-hand side, we're left with just 1. Now we're left with this as our left-hand side. This as our right-hand side. So LHS is left-hand side, RHS is right-hand side. Right. So looking at this equation right now, does this satisfy our conditions for a separable equation? So on the left-hand side, if we just ignore the derivative, is everything on the left-hand side just purely a function of y? It is, right? So we only have, one doesn't count, constants don't count. So we're only looking at y as an x. Okay? And on the right-hand side, we have just a function of x, or more importantly, is y not present on the right-hand side? And the answer is yes. Right? So on the right-hand side, we don't have any y there. On the left-hand side, we don't have any x. And so by doing this, we have succeeded. And so we can rejoice, we can say, yes, our function is separable. We can just integrate this sucker and get our solution. Okay. All right, so now that we've successfully separated the variables, let's go ahead and solve this by integration. Okay. And so the left-hand side, we're going to do integral of 1 over 1 plus y squared dy. On the right-hand side, we use integral from 1 times dx. Okay. Right, and so on the right-hand side, that one first, that will be here. So integral of 1 times dx is just integration of a constant. So that's just going to give us x. Okay. And on the left-hand side, if you remember this, then that's great. But this is actually one of those special integrals. So integral of 1 over 1 plus y squared, that is actually arctangent of y. Okay. I don't expect you to remember that. Honestly, I forgot it until I was looking at my notes again this morning, 5 minutes before the lecture. But that's one of those special interests. Normally, it's not going to be like this, so I'm not going to have something like this on the homework for the weekend. But, you know, just so happened that the exam is kind of this one. Okay, so arctangent, another way to write it is just inverse tangent. That's probably a little more clear about what it is. Okay. But remember, you know, we're not done yet. Right? Remember, whenever we do an indefinite integral, what do we have to add? We have to add our arbitrary constant. In this case, I'm going to add it to the right-hand side. All right, so from here it's just algebra. And so let's go ahead and solve this for y, or solve for y. And so to solve for y, I need to undo the arctangent. So to undo an arctangent, you just take tangent on both sides. Tangent. So on the left-hand side, we have the tangent and the arctangent. Those two are going to cancel out. So left-hand side, we have this y of x. On the right-hand side, we have a tangent x plus. And that right there is the solution to our problem. All right. Any questions on this example here? Yeah.
This is the general solution?
This is the general solution, correct. All right, let's do one more example with separation of variables, this time with an initial condition, so you can see how that is done. Let's solve this equation. So we have the equation y prime equal to minus 2xy. And so if you're not familiar with this notation, y prime, that's just kind of a shorthand way to say dy dx. Usually I'll try to write the full expression dy dx, but sometimes if you got the textbook, and sometimes in the homework assignments I might get lazy, so I might say just y prime. So y prime is simply just the first order derivative. Okay, so for this, let's solve. Let's solve for y of x. Let's solve for the particular solution. So that means this y of x is going to be subject to this initial condition. Our initial condition is y of 0 is equal to 1. And so in this case, because we're given an initial condition, we're going to be solving for particular. And so again, you know, we're given a first order differential equation here, and we're going to solve for it. I'm going to go a little bit faster this time, just because, you know, we just did kind of an example in detail, but you know, we're going to follow all the same steps. Okay, step one is going to be to separate the variables. So remember, we want to manipulate this so we have all the y terms on the left, all the x terms on the right. Okay, so in order to do that, we can see we have a 2xy on the left, on the right hand side. So let's divide by y on both sides. So on the right hand side, we have 1 over y, or left hand side, excuse me, 1 over y times y prime equal to is 2x. Okay, and by doing that simple trick of dividing by y, we've successfully separated the equation. So on the left hand side, we have a function of this y. On the right hand side, we have a function of this x. So we're good to go. All right, so let's go ahead and integrate. So if we integrate y equal to integral of minus 2x dx. So integral of 1 over y, that's also somewhat of a special integral. And so the integral of 1 over y is the natural logarithm of y, the ln of y. And on the right hand side, we have probably the most normal integral we've seen today, which is the integral of minus 2x. That's going to be a minus x squared. Remember, we're doing indefinite integrals, so we can't forget our arbitrary constant. We need to add plus c. Step 3 here is that we've integrated the differential equation, but we need to do a little bit of algebra to solve for y. So let's solve for y. And the way we do this, we need to cancel out the logarithm. And the way you cancel out a logarithm is that you have to exponentiate both sides. Right? So we take e and raise it to both sides. We have e raised to the natural logarithm of y, and e raised to minus x squared plus c. And so that e is going to cancel out that natural logarithm. And so on the left hand side, we're left with yx. On the right hand side, we have e raised to the minus x squared plus c. Remember, when you have added exponents, all that means that you are just multiplying those two terms. Raised to the minus x squared plus c. Another way we can write it is we have e raised to the minus x squared multiplied by e raised to the c. And this e raised to the c here, I'm going to simplify our life just a little bit because we know c is some arbitrary constant. We haven't really defined its value yet. E is also a constant. Its value is like 2.714 or something irrational. Okay? And so since E and C are both constants, let's simplify our life a little bit. So instead of solving for C, let's define a new constant, and we'll just call it a different name just for the sake of clarity. And so we'll call this new constant A. And And so if we replace it with that a, then it simplifies it a little bit. And so we have y of x is equal to a times e to the minus x squared. You don't have to do this. You know, this is just something that I like to do just to kind of simplify it a little bit. But you know, whenever you have a constant multiplied by a constant or a constant exponentiated by a constant, and one of those constants is still arbitrary, you can kind of just replace it with a new constant, just to kind of make it less. If you prefer to keep it in as e to the c, that's fine too. I just do it this way just to make it. All right. So what we have here is our general solution. Because we have yet to define what A is. Right. Question, yes.
We also put the x in parentheses next to the y so that it's the general solution.
I just do that just to kind of remind you that y is a function of x. But then, you can leave that. Yeah, because for these problems, it's pretty obvious what the independent solution is, or independent variable is. So you can just say y is.
I could be wrong, but isn't like when you isn't 1 over y like the integral 1 over y is supposed to be ln of the absolute value of y, or is that it?
Technically that's true too. But just for kind of convenience, I kind of dropped that. That's a good point. Yeah, you can have ln of a negative number. All right, and so let's go ahead and take the final step. And so what's different about this problem compared to our previous example is that we have an initial condition here. So our initial condition stated that y of 0 equal to 1.8. So this means when x is equal to 0, then y is equal to 1. So let's plug this into our general solution and use that to solve for All right. And so on the left-hand side, we have y of x. And so let's go ahead and set that equal to 1.8. So this right here is y of x. And on the right-hand side, we're going to plug in x is equal to 0. A multiplied by e raised to the minus x squared. So it's going to be minus 0 squared. All right. And so 0 squared is 0. Minus 0 is still 0. And so on the right-hand side, we have a times e to the 0. Okay. Another math rule that we know is that when you raise something to the 0 power, this is just equal to 1. Okay. So any number raised to a 0 power just equals to 1. And so when we simplify this, we get 1.8 is equal to a times 1. Okay. You can divide both sides by 1 if you want, but you know, it's kind of redundant. And so we get a is equal to 1.8 based on our initial condition. And so let's go ahead and plug that in. So we plug this into our final solution. We plug in a is equal to 1.8. And that's equal to, or excuse me, y of x is equal to 1.8 times e raised to the minus x squared. Here with our particular Any questions on this example here? Okay. All right, so that's separation of variables, and so that's the first way that you can use to solve differential equations, or first order differential equations. The second method that we'll go over is known as integrating factors. And integrating factors are used for situations where you have, oftentimes you use them for inhomogeneous differential equations, in particular, linear differential. Let's talk about linear. And the way that we usually solve these is integrating. All right. And so first, let's define what it means for a differential equation to be linear. All right, so for a linear differential equation, it has the following form. First, we have our derivative term. So our derivative term is still dy dx. What's different about these differential equations compared to the separable one is that we have kind of these two extra terms. So we have one term, which is p of x times y. Okay. And on the right-hand side, we have a term that is just comprised of this. It's just a function of x. Okay. And so the thing I want to highlight about this form, so now I know right now if you look at it, it's just all just variables. Okay? The thing I want to highlight here is that whenever you see y or y prime or the derivative of y here, it only appears to at a linear order. And so there's no y times y, there's no y times the derivative or a. And so if you look at dy dx here, it appears into as a first order polynomial term. Okay, in other words, it just appears at itself. And then even on the second term, if you look at y, it just also appears as a first order polynomial. In other words, another way you can say this is that all terms involving y are linear polynomial. Right, so linear polynomial order, all that means is that if you look at the exponent of each of those y terms, they should be 1. Okay. So that's what linear means. All right, so when we have a linear differential, when we have a linear first order differential equation like this, we can solve it using a technique called integrating. I'll explain that. But before I do that, I do want to have, I do want to mention one more definition, okay, which is called standard form. And so when I mention standard form of a differential equation, that means the coefficient in front of dy dx is just one. Any questions on this so far? So this form of a differential equation, even though it still seems pretty arbitrary, p of x and r of x are still relatively undefined. You'll see a lot of differential equations in this form. Okay? In particular, if we go back to kind of the very beginning of the lecture, we talk about a couple physical systems here, like the electrical circuit and the heat transfer example. Both of these kind of fall into that category of a linear differential equation. And so because it's so common, we've kind of given some particular names to the variables here that are kind of more in line with kind of what you expect from a physical system. Even next week, when we get into second order differential equations, they're going to follow kind of a similar form as well. And so sometimes, when you look at some applied math or some engineering math texts, they might refer to some of these specific terms with some kind of names that you may not be familiar with. Right, and so these names are kind of reminiscent, or they kind of refer to the fact that this differential equation, it's not just a math equation. It refers to something. And so sometimes what you'll see is that when you solve for the solution y, y is sometimes called the response of the system. Okay? So that basically tells you how the physical system is going to respond to physical stimulus. Okay? And then the function on the right-hand side often has a special name too. And so r of x, when it appears in kind of this form right here, is often called the forcing of the system, or the input of the system. And so what r of x usually represents is that it represents some kind of external force or some kind of external forcing that you're using to kind of drive the system. And so we go back to the circuit example. I actually didn't draw it into that circuit, but it is in the circuit problem in the homework. And it's going to be in the circuit example that we'll do, judging by the time, probably on Tuesday. If you had a battery in that circuit system, the way the battery would be represented as kind of a forcing or input function at R of x. All right. Any questions on this so far? Okay. All right, so let's talk about how we can actually solve this. And so these linear ODEs are often solved with a technique called integrating. All right, so what are integrating factors? So the reason we call them integrating factors is because they're kind of like an additional helper. They're kind of a helper function that lets us directly integrate this equation. All right, I'm actually- Because if you look at the way we solve our separable ODEs, we like integration. So if we're in a situation where we can directly integrate to find a solution, that's kind of the easiest thing for us to do. So unfortunately, if we look at this, the form of this function right here, let me get rid of this. We're not in a form where we can directly integrate. But we still would like that's kind of nice. And so what we say, or what we basically determine, is that if we can manipulate this equation, we can multiply it by an integrating factor, we can get it into a form where we can directly. So this mu of x here, this is our integrating factor. All right. So I'm gonna take kind of a little bit of a leap in logic. And so, because right now, our left-hand side looks something like this. Right now, the main issue is with our left-hand side. So our left-hand side is in a form that we can't directly. Let me kind of change this up. And so, what if instead our left-hand side looks something like y, yes, u, yeah, plus u, yes, y. Okay. It's a big leap, right? And so, it kind of looks like I just did some random stuff. But when we put it in this form, it actually helps us out quite a bit. Because what does this kind of look like? Right? So if we consider that y is a function of x, and our integrating factor mu is also a function of x. This looks like the result of a product. In other words, if we do d dx of y of x, u of x, and we basically carried out the product rule for that expression, then we get the expression above. Right? And what's nice about this? What's nice about this product rule form is that we can actually directly integrate this, right? So since the derivative is on the outside, it's experiencing all of the functions on the inside, we can directly integrate this. Okay. All right, so we're just about out of time. So I think, there's a little bit more to this proof, late, I was thought to do, but I'll finish on Tuesday. But in case you wanted to get started with this homework, this works out when U has a very specific expression. So this only works when U has the following form. So when U of X is equal to E raised to the integral P of X. Or if you're wondering what P of X is, P of X, that was a coefficient in front of Y in our standard linear ODE. All right, any final questions on this before we wrap it up for today? All right, so on Tuesday, we'll pick this up. I'll finish up the last details of this proof. We'll do a couple examples with integrated factors so you can see how it's done. And then we'll move on to second order. All right, so thank you everyone for coming today. I know this class is early in the morning, so I appreciate you guys coming out. If you have any questions, I'll stick around for a couple minutes after class. I have office hours at 10 o'clock today too, if you're available for that. If not, hope you guys have a good weekend, and I will see you all on Tuesday. Oh, yeah, no. Oh, no, so I just need that. I'll do the, I'll play that. Yeah, so tomorrow I'll take a look to see how. Oh. Oh, yeah. I know because, after the PPE, I know they will. So I want to make sure I have. Yeah. Austin, any final questions before I open the floor? Okay, all right, we'll see you on Tuesday.